Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to talk on module Rutherford backscattering, part 4, which is under the paper Characterization Techniques for Materials, part 2. After completing this module, the students will be able to understand the backscattering for thin film analysis, the single and multiple component thin film analysis, and single and multi-layer thin film analysis. Thin films plays an important role in making devices and also in many analytical works, including analysis of organic-inorganic interface, role of substrate in thin film deposition, low-level doping, determination with the other elements, etc. The main feature of such a spectrum is that both the front surface and the interface can be probed with better accuracy by this technique, unlike in thick sample where only front surface is recognizable. Two dependent parameters can be extracted from both the outer surface and the inner surface of the sample in a backscattering signal, and the independent parameters are: the interface gives an energy difference delta E between the adjacent edges of the signal, and the second one is the total number of counts A contained in all channels of the signal between these edges. From these, one can calculate the number of atoms per unit area contained in the thin film. The backscattering spectrum contains more than one signal for each element present in the sample, and elemental analysis can be done with each. Energy spectrum of a thin elemental film. In order to analyze the energy spectrum of a thin film, we assume that the thin film contains empty atoms of a single element per unit area. It also contains thin film with element of higher atomic mass than the substrate itself. A typical spectrum is shown in the figure below with the suppression of the background signal. The two quantities of interest are the energy width delta E of this signal and A, the total number of counts added over all channels in the signal. Both the quantities are directly related to the number of atoms per unit area contained in the film. The schematic representation of the backscattering process in thin film and corresponding backscattering signal is plotted in figure 1. Energy width delta E between the high and low energy edges of the signal. As shown in the last figure 1, particles backscattered from the surface of thin film has a kinetic energy of Ke subscript 0, those backscattered from atoms at the rear produce counts at an energy E1. The difference in energy delta E is equal to KE0 minus E1 at time t, is related to the number of atoms per unit area in the film and is given by the equation delta E is equal to epsilon bar nt, where the film is very thin. The surface approximation for E bar is adequate. From the measured value delta E and the knowledge of epsilon bar, we can determine the number of atoms per unit area denoted by Nt in the film. The next is to estimate the total number of counts in the signal. Moreover, apart from the above, other quantity that one can extract from the backscattering spectrum of a thin film is the total number of counts and is given by the equation A is equal to sum over I Hi, summed over all channels I of the signal. If Hi is expressed in terms of E1I, then the summation becomes unwieldy. The reason is that the scattering cross sections are given as a function of the energy Ei immediately before the scattering. This energy is most readily arrived at by computing the energy that the particle loses along its incident path, which is n times xi divided by cos theta times epsilon and E in, and subtracting it from the incident energy E0. So, Ei is equal to E0 minus nxi divided by cos theta 1 multiplied by epsilon times Ein. To compute A, the total number of counts in the signal, we need the yield Hi in terms of the scattering cross section at the energy Ei and the number of atoms per unit area in the ith slab. The total number of counts then become A is equal to sum over I sigma Ei omega q n tau I divided by cos theta 1. The energy spectrum of multilayered elemental films. Now, we will discuss the backscattering spectra of a sequence of elemental thin films. The analysis of the spectrum is divided into two parts. The first part is the top layer. The backscattering spectrum of this layer remains unaffected by the layers underneath. Therefore, the analysis of this layer can be done by the preceding section, where the analysis of elemental film is discussed. The other part of the elemental analysis consists of the layer that is underneath the top layer. For the films that lie beneath the top layer, the incoming incident particle has a lower kinetic energy than that falls on the surface layer. This is because the top surface layer acts as an observer and hence the energy is reduced considerably. The particles that also reach after backscattering from the second layer also has a lower energy than the backscattered particles of the top layer. A qualitative discussion of this problem is illustrated in figure 2. The film sample shown in figure consists of a film A sandwiched to a film B on the top, and both rest on elemental substrate S. For backscattering spectroscopy, the most favorable situation is when element A is heavier than B and B is heavier than S, that is, Ks is less than Kb is less than Ka. The backscattering energy spectrum for this particular case is sketched in figure 2a. The signal of A reaches to the edge Ka E0 of A, but the signals of B and of S are shifted to energies below their respective edges Kb E0 and Ks E0 because of the energy loss in the outer layer A. To illustrate this point, figure 2b represents a spectrum of a sample without layer B. Since there is no layer, the particles reaching the substrate has lower energy than that of A. The signal would have a higher energy. The signal of A is unchanged because the spectrum of a surface layer is not influenced by the underlying material. This is so because both A and B act as energy observers for S. The removal of B reduces the observing layer to the thickness of A only. The high energy edge of the signal of B now appears at Kb E0 because B is at the surface. To a first approximation, the signals of B and S are both shifted toward higher energies by an amount that roughly equals the width of the observer signal A. The schematic representation of the backscattering spectrum of a bilayered film on a substrate S is represented in the figure 2. Here, the monoisotopic element A is the heaviest, P is the intermediate, and S is the lightest. The spectrum for a sample without the intermediate layer B is shown in figure B, and the spectrum for a sample without the top layer A is represented in figure C. The energy spectrum of a homogeneous thin film containing more than one element or compound films will focus on the analysis of a thin film which is composed of many elements. This is different than the single element thin films in many ways. Firstly, due to the presence of different constituent atoms, the energy of the incident particle decreases as there are many interactions with the other elements of the film. As a result, the stopping cross-section depends on the composition of the film and is therefore initially this quantity is unknown. Similarly, the backscattered electron also carry different kinetic energy due to the presence of dissimilar atoms. This mass is different for the various elements in the film. The stopping cross-section varies with energy so that the energy of the scattered particles would depend on the type of atom it interacts during the collision. Suppose that the film contains two elements A and B in the atomic ratio AMBN. The backscattering spectrum of such a homogeneous film with two elements is sketched in figure 3. The two signals are observed corresponding to scattering from the heavy atom A and the light atom B. The schematic representation of the backscattering process in a self-supporting compound thin film sample and the resulting backscattering spectrum is shown in figure 3. It shows the meaning of the symbols used in the text. The energy width delta E between high and low energy edges of the signal. The energy widths delta E subscript A and delta E B generally differ by as much as 10% in spite of the fact that there is only one film thickness I, because generally epsilon A at the interface AB is not is equal to epsilon B at AB. Since the depth to energy conversions are not the same for the two signals, the difference in energy is created. Hence, the number of molecules per unit area or the molecular units per unit area in case of a mixture can be found in two different ways. N of AB time T is equal to delta E A divided by epsilon A AB, or the NABT is equal to delta E B divided by epsilon B AB. The total number of counts in the signals. The comparison of the film is generally unknown. This means that epsilon A AB and epsilon B of AB cannot be computed, even when the elements A and B are known, because M and N are not known. These two equations also cannot determine the number of molecules or molecular units per unit area in the film. However, the total number of counts in a signal is related to the number per unit area of the atoms in the target that generate the signal. The ratio AA divided by AB of the total number of counts AB and AB in the spectrum represented in the earlier figure is therefore related to the ratio m divided by n. The connection between the total numbers of counts AA and AB in signals A or B and the number NA ABT and NA ABT of atoms per unit area in the film thus constitutes the point of main interest in the backscattering spectrum of the figure earlier shown. The energy immediately before the collision is E is equal to E0 minus N ABX divided by cos theta 1 whole multiplied by epsilon AB E bar IN, and the total number of counts AA is the signal of A can be expressed as AA is equal to omega q m n AB divided by cos theta 1 whole multiplied by integration from 0 to t sigma A the function of E times Tx. The ratio of signal heights in surface energy approximation. The ratio m divided by n of the relative concentrations m and n of the elements A and B in a homogeneous bi-elemental film can also be obtained from the heights h A0 and h B0 of the signals of A and B. The scattering from the top surface layer of such a sample is the same as for a bulk sample. Therefore, two different ways of finding the ratio m divided by n. One approach uses the total number of counts in the signal of A and B, and the stopping cross-section factors need not be known. The other approach uses the height of the signals at their high energy edge. In this case, the ratio epsilon subscript A superscript AB divided by the epsilon subscript B superscript AB of the stopping cross section factors enters into the result. That ratio is usually close to unity and can be attained by iteration. From the knowledge of m divided by n, the relative compositions m and n follow with the condition that m plus n is equal to 1. It is not possible, however, to state that the sample is composed of the chemical compound AMBN even if m and n are fractions of small integers. Backscattering spectra only provide information on relative atomic composition, how these atoms are combined, that is, the chemical constitution of the sample must be deduced from other experiments such as chemical analysis or X-ray diffraction. Now let us study about the energy spectrum of multilayered films containing more than one element or layered compound films. This section combines the subject of multilayered elemental films with that of compound films having more than one element. The combinations are many. For example, multilayer plus compound film on an elemental film, the heaviest element being either on the top layer or underneath it. The formula describing the spectrum of all these examples will be different in each case, but the concepts from which they are derived are the same in every case. We shall therefore give a detailed treatment of one particular case only to demonstrate the procedure through that example. In general, the spectrum of a multilayered sample with compound films is complex because the signals of the various elements in the layers overlap. To identify certain features of the spectrum with signals generated from a specific element in a specific layer of the target is usually a non-trivial task. This job is greatly facilitated if several spectra of the same sample are taken under different experimental conditions. Sample normal and tilted with respect to the incident beam, several incident energies, etc. We are not concerned here with these questions of proper interpretation of a spectrum. Rather, we assume that the subdivision of the spectrum in its individual signals has been accomplished already. It is then convenient for the discussion to assume that the signals of the various elements do not overlap. The top layer of a multilayered sample can be analyzed as described above if it is a compound film, since the underlying layer do not affect the spectrum of the top layer. Other than that, possibly an overlap of signals. There are top layer, and the top layer is assumed to be elemental, but as it was pointed out in the end of that section, the treatment is the same for a compound observer. After this second layer has been analyzed, the first two layers together are considered as one observer to the third layer. The analysis of that layer is undertaken next, and the process is iterated as necessary until all the layers have been analyzed. Although this process is logically simple, its execution and the formulas rapidly become long and cumbersome. A comparison with numerically computed spectra may be easier. This process is demonstrated in detail for the particular case of a sample composed of a thin film of element A on top of a compound film of composition AMBN. This situation is encountered when a thin film of A reacts at the interface with the substance B and starts to form a compound AMBN. A schematic diagram of the backscattering energy spectrum, such as sample shown in figure 4. For simplicity, A is assumed to be the heavier element of the two, and the total amount of A is taken to be small enough so that no signals overlap. In the superscripts, the compound AMBN is abridged to AB. Note that superscripts identify the medium and that subscripts give the element to which the quantity refers. The succeeding subsections discuss the main quantities of interest in this spectrum. The schematic representation of the backscattering process in a sample composed of a thin surface film of a monoisotropic heavy element A, a substrate of monoisotropic light element B, and a compound layer AMBN, and the resulting backscattering spectrum is shown in figure 4. Also, the figure shows the meaning of the symbols used in the text. So students, let us now summarize what we have learned in this module. In this session, we have briefly described the elemental analysis of a thin film by backscattering spectrum. Various compositions of thin films, including single layer, multi-layer, single and multi-elemental thin films, have been discussed in detail. It gave an idea about how to analyze the backscattering spectrum in case of thin film with composite structures. Thank you.